Polyacrylic acid, PAA, is a synthetic, water-compatible polyelectrolyte produced from acrylic acid, AA. Its polymer backbone contains pendant carboxylic acid groups that impart a combination of hydrophilicity, hydrogen bonding capability, ionization, adhesion, and strong pH-dependent swelling. These characteristics have made PAA an important functional polymer in biomedical formulations, water management, coatings, adhesives, energy storage, and electronic materials. PAA can also be incorporated into hydrogels, interpenetrating polymer networks, IPNs, nanoparticles, microspheres, films, and other architectures to tailor its physicochemical behavior. The sodium salt, sodium polyacrylate, is the ionized counterpart of PAA and is particularly important as a superabsorbent polymer, SAP. The presence of sodium carboxylate groups generates a highly hydrophilic polyelectrolyte capable of absorbing and retaining very large quantities of water. Consequently, PAA and sodium polyacrylate occupy complementary technological niches. PAA is especially valuable where protonation, adhesion, and pH responsiveness are required, whereas sodium polyacrylate is particularly effective in water absorption, dispersion, and ion-mediated applications. Synthesis and polymer chemistry. PAA is conventionally synthesized by free radical polymerization of acrylic acid. Common initiators include persulfates and 2,2'-azobasis-O-butyronitrile, AIBN. Reaction temperature, initiator concentration, monomer concentration, solvent, and reaction atmosphere strongly influence molecular weight and polymer architecture. Excessively high temperatures can increase radical concentration and accelerate termination, resulting in oligomer formation rather than high molecular weight polymer. Controlled radical polymerization has expanded the ability to regulate PAA molecular architecture. Reversible addition fragmentation chain transfer, RAFT. Polymerization employs chain transfer agents, such as trithiocarbonates or xanthates, to establish a reversible addition fragmentation equilibrium and control molecular weight and chain end functionality. Atom transfer radical polymerization, ATRP, has likewise been investigated for producing better-defined acrylic polymers. Plasma-assisted polymerization represents another emerging route for preparing acrylic acid-derived functional coatings. Sodium polyacrylate can be prepared either by polymerizing acrylic acid followed by neutralization with sodium hydroxide, or by neutralizing acrylic acid before polymerization. Aqueous solution polymerization is particularly convenient for producing water-soluble acrylate polymers. Another approach involves alkaline hydrolysis of acrylate polymers, followed by conversion to the sodium carboxylate form. Structure and physicochemical properties. The defining chemical feature of PAA is its high density of pendant carboxylic acid groups. In acidic media, these groups remain predominantly protonated, whereas above the pKa of acrylic acid, approximately 4.25, they progressively ionize to COO- groups. Ionization generates electrostatic repulsion between neighboring polymer segments and increases the osmotic pressure within a polymer network, producing substantial chain expansion and swelling. Thus, PAA is a prototypical pH-responsive polyelectrolyte. The extent of swelling depends on molecular weight, degree of cross-linking, pH, ionic strength, counterion identity, and polymer concentration. In the non-ionized state, swelling is primarily governed by polymer-solvent interactions and network elasticity. Ionization introduces an additional electrostatic contribution that can dramatically increase water uptake. In sodium polyacrylate, the permanently associated sodium counterions and carboxylate groups produce high hydrophilicity and osmotic swelling. PAA also possesses substantial hydrogen bonding capability. Its carboxylic acid groups can interact with hydroxyl, amine, amide, and other hydrogen bonding functionalities in biological and synthetic substrates. These interactions contribute to adhesion and enable PAA to function as a component of polymer blends, IPNs, composite hydrogels, and surface coatings. FTIR spectroscopy provides a convenient means of identifying PAA. A characteristic carbonyl absorption near 1,714 centimeters to the power of -1 is associated with the carboxylic acid group, while additional bands arise from CO, OH, and CH2 vibrations. Molecular weight and structural characterization can additionally employ NMR, chromatography, and related spectroscopic techniques. Biomedical applications. Polyacrylic acid is particularly attractive for biomedical applications because its carboxyl groups provide controllable interactions with biological molecules and surfaces. Its principal biomedical attributes include mucoadhesion, water absorption, pH responsiveness, and the ability to form physically or chemically cross-linked hydrogels. Drug delivery. AA-based hydrogels can function as reservoirs for small molecule drugs, proteins, and peptides. The polymer can be formulated as injectable gels, films, tablets, microspheres, nanoparticles, and nanofibers. Drug release can be regulated through changes in swelling, diffusion, polymer relaxation, and ionization. The pH sensitivity of PAA is particularly important for controlled drug delivery. At low pH, protonated carboxylic groups favor a relatively contracted polymer structure. At higher pH, ionization to COO- produces electrostatic repulsion and network expansion. This behavior can be exploited to construct systems that undergo different swelling and drug release rates in different physiological environments. Mucoadhesion and ocular delivery. PAA is an effective mucoadhesive polymer because its protonated carboxylic acid groups can form hydrogen bonds with functional groups within mucin glycoproteins. Interaction with mucin can increase interfacial viscosity and prolong polymer residence on mucosal surfaces. This behavior is particularly relevant to ocular, nasal, and topical drug delivery. PAA-based materials have also been investigated as biomimetic tear fluid systems because of their strong water retention capability. Tissue engineering and regenerative medicine. Cross-linked PAA networks can mimic important characteristics of hydrated biological matrices. PAA-containing hydrogels and IPNs provide high water content, tunable mechanical properties, and functional carboxyl groups capable of interacting with proteins and cells. These properties have stimulated research into tissue engineering scaffolds, regenerative medicine, and cell interactive materials. Biosensors and nanomedicine. The ionizable carboxyl groups of PAA provide chemically addressable sites for immobilizing biomolecules and nanoparticles. PAA-containing nanoplatforms, including nanoparticles, nanofibers, and nanoconjugates, have consequently been investigated for biosensing, bioimaging, and anti-cancer drug delivery systems. Changes in pH or electrical stimuli can also modulate polymer conformation, providing mechanisms for responsive sensing and controlled release. PAA-based hydrogels and artificial muscles. Hydrogels are three-dimensional polymer networks capable of retaining large quantities of water. PAA is particularly suitable for hydrogel construction because its carboxylate groups generate strong osmotic and electrostatic swelling forces after ionization. PAA hydrogels can be prepared by direct cross-linking, copolymerization, or formation of IPNs. Copolymerization with other monomers allows the incorporation of hydrophobic, ionic, thermoresponsive, or mechanically reinforcing components. In an IPN, a second polymer network is formed within a pre-existing network. A full IPN contains two cross-linked networks, whereas a semi-IPN consists of a network formed in the presence of an uncross-linked polymer. Because swelling can be controlled by pH, ionic strength, and electrical stimulation, PAA-containing gels have also been explored as artificial muscles and electroactive actuators. Early work involving cross-linked PAA demonstrated the potential of chemically induced volume changes for mechanical actuation. At the same time, modern electro-responsive PAA assemblies extend this concept toward soft robotics and adaptive devices. Superabsorbent polymers. Sodium polyacrylate is one of the most important synthetic superabsorbent polymers. Its carboxylate-rich chains strongly interact with water, while electrostatic repulsion between negatively charged polymer segments promotes expansion of the network. Cross-linking prevents complete dissolution and converts the polymer into a three-dimensional absorbent network. Depending on molecular weight, cross-link density, particle morphology, and formulation, sodium polyacrylate can absorb and retain hundreds of times its own mass in water. The source material reports absorption capacities ranging from approximately 100 to 1,000 times the polymer mass. This combination of absorption and retention makes sodium polyacrylate useful in disposable hygiene products, absorbent pads, water-retaining gels, fire-retardant formulations, and aqueous thickeners. The swelling behavior, however, is strongly affected by dissolved salts because counterions screen electrostatic interactions and reduce osmotic swelling. Semiconductor and electronic materials applications. PAA has increasing importance in electronic materials processing because its carboxylate functionality enables interactions with metal ions, inorganic particles, and semiconductor surfaces. A particularly important application is chemical-mechanical planarization, CMP, a critical semiconductor manufacturing process. In CMP, ultra-pure, low molecular weight PAA can function as a stabilizer and dispersant in aqueous abrasive slurries used to planarize silicon wafers. Effective dispersion prevents abrasive particle agglomeration and contributes to control of surface defects and wafer uniformity. PAA also participates in wet processing formulations through its ability to coordinate or interact with metal ions and stabilize aqueous dispersions. Such interactions can be exploited to regulate particle aggregation, surface chemistry, and contaminant removal during semiconductor processing. Beyond conventional wafer processing, PAA is relevant to energy and flexible electronics. PAA and sodium polyacrylate can serve as polymeric binders for silicon and graphite electrodes in lithium-ion batteries. Their mechanical and polar character enables strong interactions with electrode particles while helping accommodate dimensional changes associated with repeated lithiation and delithiation. PAA-containing conductive hydrogels are additionally being developed for flexible and wearable electronics. Their combination of water retention, ionic conductivity, deformability, and self-healing capability makes them attractive for electronic skin, soft robotics, and human-machine interactive sensors. PAA can also act as a film-forming or binding component in specialty encapsulation systems for electronic components. An emerging area is laser-induced graphene, LIG. PAA can serve as a soluble, film-forming precursor or matrix for introducing dopants into laser-written carbon structures. Its ability to distribute dopant species relatively uniformly can modify the electrical characteristics of the resulting LIG composites and broaden their potential for energy storage and electronic applications. Agricultural applications. Sodium polyacrylate has a long history in agriculture. Its use as a soil conditioner emerged in the 1950s, when sodium polyacrylate-containing materials were investigated for improving soil aggregation, porosity, and permeability. Historical work reported improvements in these properties and associated increases in crop productivity at relatively low polymer concentrations. The principal agricultural mechanism is water management. When incorporated into soil, cross-linked polyacrylate particles absorb irrigation or rainfall water and subsequently release part of the stored water as the surrounding soil dries. This can increase local water availability, reduce irrigation frequency, and potentially improve water use efficiency. The same polymer can also modify soil structure through interactions with mineral particles and dissolved ions. The effectiveness of polyacrylate soil amendments depends strongly on soil composition, salinity, climate, polymer concentration, and degradation or persistence behavior. Consequently, practical agricultural formulations must balance water retention with cost, long-term soil compatibility, and environmental considerations. PAA has also been investigated more broadly as a soil ameliorant and as a polymeric component in water management technologies. Other functional applications. The high density of ionizable groups gives PAA utility beyond biomedical and electronic applications. It can function as a dispersant, thickener, rheology modifier, and drag-reducing polymer. Its metal-binding capability also makes it attractive for water treatment, including heavy metal capture and dye removal. The ability to combine PAA with other polymers further expands its application space. Copolymerization and IPN formation allow its strong hydrophilicity and pH responsiveness to be combined with mechanical strength, thermal responsiveness, electrical functionality, or specific biological interactions. This molecular and network-level tunability is one of the principal reasons PAA remains an important platform polymer in advanced functional materials. In conclusion, polyacrylic acid and sodium polyacrylate represent closely related but functionally distinct members of the acrylic polyelectrolyte family. Their high density of carboxylic acid or carboxylate groups provides a unique combination of water affinity, ionization, hydrogen bonding, adhesion, dispersion, and stimulus-responsive swelling. These properties can be manipulated through molecular weight, cross-link density, neutralization degree, copolymerization, and network architecture. PAA is particularly valuable for pH-responsive biomedical systems, mucoadhesive drug delivery, tissue engineering hydrogels, biosensors, and responsive nanomaterials. Sodium polyacrylate, by contrast, exploits the same ionic chemistry primarily for extreme water absorption, making it a major superabsorbent material with applications in hygiene products, water management, and agriculture. In semiconductor manufacturing, highly purified PAA has specialized roles as a dispersant and stabilizer in CMP and wet processing formulations. At the same time, PAA-derived binders and conductive hydrogels extend its relevance into batteries and flexible electronics. The versatility of these polymers ultimately originates from a relatively simple chemical structure combined with highly tunable polyelectrolyte behavior. Continued development of controlled polymerization, network engineering, nanostructuring, and hybrid material approaches is likely to expand PAA-based materials toward increasingly sophisticated biomedical, electronic, environmental, and agricultural technologies.